United States Environmental Protection Agency, Office of Water, Washington, D.C. EPA 932-F-99-067, September 1999. EPA Wastewater Technology Fact Sheet. Intermittent sand filters. Intermittent sand filters, ISFs, have 24-inch deep filter beds of carefully graded media. Sand is a commonly used medium, but anthracite, mineral tailings, bottom ash, etc., have also been used. The surface of the bed is intermittently dosed with effluent that percolates in a single mass through the sand to the bottom of the filter. After being collected in the underdrain, the treated effluent is transported to a line for further treatment or disposal. The two basic components of an ISF system are a primary treatment unit, a septic tank or other sedimentation system, and a sand filter. Figure 1 shows a schematic of a typical ISF. Figure 1, typical cross-section of an intermittent sand filter. ISFs remove contaminants in wastewater through physical, chemical, and biological treatment processes. Although the physical and chemical processes play an important role in the removal of many particles, the biological processes play the most important role in sand filters. ISFs are typically built below grade in excavations 3 to 4 feet deep and lined with an impermeable membrane where required. The underdrain is surrounded by a layer of grounded gravel and crushed rock, with the upstream end brought to the surface and vented. Pea gravel is placed on top of the graded gravel, and sand is laid on top of the pea gravel. Another layer of graded gravel is laid down, with the distribution pipes running through it. A flushing valve is located at the end of each distribution lateral. Lightweight filter fabric is placed over the final course of rock to keep silt from moving into the sand while allowing air and water to pass through. The top of the filter is then backfilled with loamy sand that may be planted with grass. Buried ISFs are usually designed for single homes. Some common types of these sand filters are listed below. Gravity discharge ISFs. The gravity discharge ISF is usually located on a hillside with the long axis perpendicular to the slope to minimize the excavation required. Because the effluent leaving the sand filter flows out by gravity, the bottom of the sand filter must be several feet higher than the drain field area. To achieve the difference in elevations, a sand filter must be constructed partially above ground. Pumped discharge ISFs. The pumped discharge sand filter is usually sited on level ground. Its location in relation to the drain field is not critical since a pump located within the sand filter bed allows effluent to be pumped to a drain field at any location or elevation. Discharge piping goes over, not through, the sand filter liner, so the integrity of the liner is protected. Bottomless ISFs. The bottomless ISF has no impermeable liner and does not discharge to a drain field, but rather directly to the soil below the sand. Table 1 shows the typical design values for ISFs. These values are based on past experience and current practices and are not necessarily optimum values for a given application. See Table 1, Typical Design Criteria for ISFs. Advantages and disadvantages. Advantages. ISFs produce a high quality effluent that can be used for drip irrigation or can be surface discharged after disinfection. Drain fields can be small and shallow. ISFs have low energy requirements. ISFs are easily accessible for monitoring and do not require skilled personnel to operate. No chemicals are required. If sand is not feasible, other suitable media can be substituted and may be found locally. Construction costs for ISFs are moderately low, and the labor is mostly manual. The treatment capacity can be expanded through modular design. ISFs can be installed to blend into the surrounding landscape. Disadvantages. Disadvantages. The land area required may be a limiting factor. Regular but minimal maintenance is required. Odor problems could result from open filter configurations and may require buffer zones from inhabited areas. If appropriate filter media are not available locally, costs could be higher. Clogging of the filter media is possible. ISFs could be sensitive to extremely cold temperatures. ISFs may require a National Pollutant Discharge Elimination System permit, NPDES permit, when the effluent is surface discharged. Performance. Sand filters produce a high-quality effluent with typical concentrations of 5 milligrams per liter or less of biochemical oxygen demand, BOD, and suspended solids, SS, as well as nitrification of 80% or more of the applied ammonia. Phosphorus removals are limited, but significant fecal coliform bacteria reductions can be achieved. The performance of an ISF depends on the type and biodegradability of the wastewater, the environmental factors within the filter, and the design characteristics of the filter. The most important environmental factors that determine the effectiveness of treatment are media reaeration and temperature. Reaeration makes oxygen available for the aerobic decomposition of the wastewater. Temperature directly affects the rate of microbial growth, chemical reactions, and other factors that contribute to the stabilization of wastewater within the ISF. Filter performance is typically higher in areas where the climate is warmer compared to areas that have colder climates. Discussed below are several processes, designed parameters that affect the operation and performance of ISFs. The degree of pretreatment. An adequately sized, structurally sound, watertight septic tank will ensure adequate pretreatment of typical domestic wastewater. Media size. The effectiveness of the granular material as filter media is dependent on the size, uniformity, and composition of the grains. The size of the granular media correlates to the surface area available to support the microorganisms that treat the wastewater. This consequently affects the quality of the filtered effluent. Media depth. Adequate sand depth must be maintained in order for the zone of capillarity to not infringe on the upper zone required for treatment. Hydraulic loading rate. In general, the higher the hydraulic load, the lower the effluent quality for a given medium. High hydraulic loading rates are typically used for filters with a larger media size or systems that receive higher quality wastewater. Organic loading rate. The application of organic material in the filter bed is a factor that affects the performance of ISFs. Hydraulic loading rates should be set to accommodate the varying organic load that can be expected in the applied wastewater. As with hydraulic loading, an increase in the organic loading rates results in reduced effluent quality. Dosing techniques and frequency. It is essential that a dosing system provide uniform distribution, time, and volume of wastewater across the filter. The system must also allow sufficient time between doses for reaeration of the pore space. Reliable dosing is achieved by pressure-dosed manifold distribution systems. Operation and maintenance. The daily operation and maintenance, O&M, of large filter systems is generally minimal when the ISF is properly sized. Buried sand filters used for residential application can perform for extended periods of time. Primary O&M tasks require minimal time and include monitoring the influent and effluent, inspecting the dosing equipment, maintaining the filter surface, checking the discharge head on the orifices, and flushing the distribution manifold annually. In addition, the pumps should be installed with quick disconnect couplings for easy removal. The septic tank should be checked for sludge and scum buildup and pumped as needed. In extremely cold temperatures, adequate precautions must be taken to prevent freezing of the filter system by using removable covers. Table 2 lists the typical O&M tasks for ISFs. Table 2, recommended O&M for ISFs. Pretreatment. O&M requirement depends on process. Remove solids from septic tank or other pretreatment unit. Dosing chamber. Pumps and controls. Check every 3 months. Timer sequence. Check and adjust every 3 months. Opportunities. Check every 3 months. Filter media. Raking. O&M requirement as needed. Replacement. Skim sand with heavy incrustations occur. Replace sand to maintain design depth. Other for filter media. Weed as needed. Monitor or calibrate distribution device as needed. Also, prevent ice sheeting. Applicability. An assessment conducted in 1985 by the U.S. Environmental Protection Agency of ISF systems revealed that sand filters are a low-cost, mechanically simple alternative. More recently, sand filter systems have been serving subdivisions, mobile home parks, rural schools, small communities, and other generators of small wastewater flows. Sand filters are a viable addition or alternative to conventional methods when site conditions are not conducive for proper treatment and disposal of wastewater through percolative beds or trenches. Sand filters can be used on sites that have hollow soil cover, inadequate permeability, high groundwater, and limited land area. Placer County, California. Placer County, California, in the last 20 years, has had to develop their land with on-site systems due to the popularity of their rural homes at elevations of 100 to 4,000 feet. The county extends along the western slope of the Sierra Nevada mountains from Lake Tahoe through the foothills and into the Great Central Valley. Large areas of the county have marginal soil quality, shallow soil depth, and shallow perched groundwater levels. In 1990, a program was initiated to permit the use of the Oregon type ISF system on an experimental basis to elevate their performance and other related factors. The ISF system used in this study had the following components: A conventional septic tank followed by a separate pump vault. A plywood structure with a 30 millimeter PVC liner for the filter and appurtenances. 24 inches deep of carefully graded clean sand. A gravel overlayer and underlayer containing the pressurized piping manifold to distribute the septic tank effluent over the bed, and a collection manifold to collect the wastewater. The dimensions of the filter for both 3 and 4 bedroom homes were 19 feet by 19 feet at a design loading rate of 1.23 gallons per square foot per day. Summarized below in Table 3 are the results obtained from 30 ISF systems serving single-family homes during warm and cold weather. The results of this study indicate that ISF systems showed a marked improvement in their effluent quality over septic tanks. Although the systems performed well, nitrogen and bacteria were not totally removed, which indicates that ISF systems should be used only where soil types and separations from the groundwater are adequate. Other findings show that early involvement of stakeholders is vital to the program's success. Effective system maintenance is essential, and the local learning curve allows errors that adversely affect system performance. Boone County, Missouri. A pressure-dosed ISF was installed and monitored on the site of a 3-bedroom single-family residence in Boone County, Missouri. The sand filter, followed by a shallow drain field, replaced a lagoon and was installed to serve as a demonstration site for the county. The soil condition at this site is normally acceptable for septic tank effluent, but the top 30 to 35 centimeters had been removed to construct the original sewage lagoon. The existing septic tank was found to be acceptable and was retrofitted with a pump vault and a high head submersible pump for pressure dosing the sand filter. The sand filter effluent drained into the pump vault in the center of the sand filter, which then pressure dosed 2 shallow soil trenches constructed with chambers. The system was installed in October 1995, and the performance was monitored for 15 months. The sand filter used in this study consistently produced a high-quality effluent with low BOD, suspended solids, and ammonia nitrogen, NH4-N. Table 4 lists the various parameters studied. The aerobic environment in the sand filter is evident from the conversion rate of NH4-N, ammonia nitrogen, to nitrate nitrogen, NO3-N, that also resulted in no other problems. The fecal coliform numbers were consistently reduced by 4 log units. Table 4, effluent characteristics of the ISF in Boone County, Missouri. The average electricity use by this system was 9.4 kilowatt hours per month, and the cost of operating two pumps in the system has been less than 70 cents per month. The high quality effluent produced by the sand filter also reduced the size of the absorption area. The cost of an ISF system depends on the labor, materials, site, capacity of the system, and characteristics of the wastewater. The main factors that determine construction costs are land and media, which are very site specific. Table 5 is an example of a cost estimate for a single family residence. Energy costs are mostly associated with the pumping of wastewater onto the filter. The energy costs typically range between 3 to 6 cents per day. Consequently, the energy costs of sand filters are lower than most small community wastewater processes, except for lagoons.